So in this class we start discuss about vector calculus. So suppose we have a function f, usually we call r. So r is a function from r to r3. So r3 is nothing but 3-dimensional space. So usually we call this because if you take given any element, we have to assign some order triple, that is called a vector valued function. Okay, so this function is called a real valued vector valued function. Okay, or simply say vector valued function. Vector valued function, because the range is just some vector. Vector means it's a 3 tuples. Okay, so that's why we called vector. So usually we denote the function is r, this arrow. Okay, so it's a function from r to r3. So therefore given any element in r, usually we call t. This t denotes time. Why we use this t? Because so many applications depend upon the time. That's why we use the notation t. For given any t in the r, we have to assign some order triple. Okay, so maybe we can denote, we can assign something. Maybe we can denote x of t is the first coordinate, and then y of t is the second coordinate, z of t is the third coordinate. So given any t in t, we have to assign some order triple. Such a function is called a vector valued function. Usually we denote r cap, r vector. So or we can represent this as in terms of I and j k. Okay, because if you take any if you look at the 3-dimensional space, this is usually x-axis, we denote I vector, j vector, k vector. Okay, so this is z-axis, this is x-axis, this is y-axis. Okay, so therefore this can be written as x of t times I vector plus y of t into j vector plus z of t into k vector. But each x of t is a function from, is a real number. Okay, just to x of t we can look at as a function. Okay, is a function from r to r. Okay, just this is a real number, this is a real number. So maybe we can see x is a function from x to r, y is also a function from x r to r. So you define it to be x of t equal to x of t, that coordinate. Okay, anyway, so this is a vector valued function. Now so already we discussed functions of 2 variable, that is f is a function from r2 to r2, and then we can discuss about continuity and then derivative of this function. And that case we take the domain is just r. Now we take the domain is r3. Now we can discuss about the continuity and then derivative of this vector valued function. Okay, so what do you mean by limit actually? So next definition, limit of this vector valued function. So limit of vector function, or simply say vector function, limit of a vector function. So how to define the limit of the function at the point a? So that is, what is the limit t approaches to some point a, r cap, r vector of t. So that is nothing but the same definition we discussed earlier. So you have to take the limit term by term. So that is nothing but limit t goes to a, x of t into I vector, or you can take I vector outside, because I vector is just a notation. So you can take I vector first and then take the limit. Okay, so that is not an issue. So this is equal to I vector into limit x tends to e, t tends to a, x of t, plus j vector into limit t goes to a, y of t, plus k vector into limit t goes to a, z of t. So this is a limit of a vector function at the point a. We have to take term by term, but we know that this is a now this part is a just a real valued function. We know how to find the limit. So what is the meaning of this? So limit t goes to a, that x of t is nothing but, so that is a limit h goes to 0. We can take that x of t plus h minus x of t, or if you take a, so f x of a plus h minus x of a by h. We take t minus a equal to h. Okay, so this is a limit. if the limit exists, then this limit, we know this. Okay, for the function of single variable real valued function, this we know that. Okay, so just you have to multiply with I to this one, and then multiply with this to this function, and then finally we get a solution. Okay, now what about the continuity of a vector valued function? So the next one is what when we say the function is continuous. So continuity of vector valued function. Continuity of vector function. So same thing. So in the case limit x close to a, f of x equal to f of a, then we say f is continuous. Similarly here, so if the limit, so we say a vector function r is continuous at the point a. So a vector function r vector is continuous at the point a if the limit t goes to a, r vector t should be r vector of a. Okay, so this is happened, then we say the vector function r is continuous at the point e. Okay, now we discuss limit function and then continuity of a vector function. Now what is the derivative of vector function? When we say the vector function is differentiable at the point some a. So the next one is derivative of a vector function. So again, suppose we denote the derivative of the vector is r dash. Okay, so the derivative r dash vector. So the derivative r dash vector. Okay, this is nothing but of a vector. The derivative, this we denote this notation of a vector function r cap, r vector of a vector function r vector. So the derivative of this we denote r dash. Okay. Now this similarly what we defined in the real case, real valued function. So that is we denote dr vector by dt at the point t is nothing but just we denote r dash vector of t is the limit h goes to 0 r cap of t plus h minus r cap of r vector of t by h. That is the usual definition for derivative. So what is the meaning of this? You have to take the limit term by term, that is x of t, y of t, z of t, same thing. So if the limit exists, then we say the vector function is differentiable and is denoted by r dash vector at the point t. Okay. So again, there are some properties for this vector. If you take the sum of two vectors, the differential derivative is nothing but you have to sum separately. So these are all some standard results. Some standard results. Okay. So suppose we have a two vector valued function. What is the derivative of the sum of two function? So that is d by dt of, if you have two vector function u and then v is nothing but you have to differentiate separately and then sum. So du vector by dt plus dv vector by dt, and then if you take subtraction also same will work. So therefore I can put plus or minus. Now the second in product, suppose we have a two vector function u and v, what is the derivative of the product one? So first you have to fix the vector u and then differentiate another vector plus differentiate the vector u with respect to t, and then we have to fix thing. So this is a second property result. Now the third one is, so in the vector we can have a sum of two vectors, we can take product of two vectors, that is this is the dot product. Okay, Now the third one is Cartesian product of two vectors is also defined. So what is the derivative of the Cartesian product or vector product? Vector product. So what is the derivative of this? You have to fix the first vector cross differentiate the second vector. So the order is very important. So plus differentiate the first vector with respect to t cross v vector. Okay, don't write v cross du by dt. Okay, so because a cross b need not be b cross a, but in the dot product a dot b equal to b dot a. So the dot product is not an issue for the order, but in the vector product the order is very important. Okay, so e is always u is first. So that's why I can take u first here and then take here u also first, the derivative of u. So the order is very important for the vector product. Now, and then the fourth one is, suppose you have some scalar function, then the derivative of pi also function of t, but some scalar. Okay, so into some u vector is nothing but again same thing, we have to fix pi and then differentiate u plus differentiate pi with respect to t into u vector. So and so on, so many results are there. Again similarly for quotient of two vector function, what is the derivative? That is d by.
So the phi is not constant, sir.
The pi is not constant, but it's a scalar valued function. I will define what is scalar valued function. Okay, so the output is scalar, then we say it's a scalar valued function. Okay, for example volume.
So result will be scalar, sir. Any constant number.
But it's a function of t. Okay, I will explain later. Okay, this fourth one. Okay, maybe if you understand what is the scalar valued function, you can see what is this one. Okay, now what is the derivative of quotient of two vector? Okay, one is scalar. So if you take u vector by s is a some scalar valued function. Okay, so this is nothing but s square. You have to fix x and then differentiate u with respect to t minus differentiate u vector into differentiate s with respect to t, where s is a scalar valued function. Okay, it's not a scalar. Okay, actually, so there is a difference. If the range is R3, then this is vector valued function. If the range is R, then it's a scalar valued function. Okay, it need not be constant. Just to say scalar valued function depending upon the range. If suppose the function is 3 coordinates, then it's a vector valued function. Suppose the function is single coordinates, then we say it's a scalar function. Okay, just a number. Maybe it's different depending upon the points. Okay, so it's not just a constant, it's a scalar valued function. So s is just I'm stating scalar. So scalar means what? It's a scalar valued function. It's not a constant function. Okay, there is some difference. Okay, so these are all some basic things. So similarly, we can define what is the partial derivatives of a vector valued function. Suppose sometimes the domain itself we have a function of 3 variable. In that case, what is the partial derivatives? Same definition, you have to vary only x and then take the limit. So partial derivatives of a vector function. So partial derivatives, you got to differentiate r partially with respect to x. So what is the definition? So usually we denote dou r vector by dou x vector. So dou x. Okay, so this is nothing but you have to expand only the real the first coordinate. So suppose assume that r vector is suppose f of x comma y comma z. Okay, now what is dou r by dou x? You have to take limit some delta x goes to 0 or h goes to 0. You can take anything. So limit h goes to 0, f of x plus h only where the first coordinate, all other coordinates are fixed, minus f of x y z by h. If the limit exists, then we say this is a partial derivatives of r with respect to x. Similarly, we can define what is dou r vector by dou y is again, so limit h goes to 0, f of x comma y plus h comma z minus f of x y z by h. If the limit exists, then we say it's a partial derivatives of r with respect to y. Similarly, we can differentiate r with respect to z is the last coordinate you have to vary. So limit h goes to 0, f of x comma y comma z plus h minus f of x comma y comma z by h. Okay. So these are all partial derivatives of r with respect to x, y, z and y. So now we define what is the total derivative. So that is total derivatives means what? dr. So the total derivative of r. So the total derivative of the vector function r is also defined as dr vector. So defined as dr vector is nothing but just you have to take the partial derivative, that is dou r vector by dou x into dx plus dou r vector by dou y into dy plus dou r vector by dou z into dz. So this is a total derivative of the vector family function r. Now we discuss some example and then we move to the next one. Exercise. So a particle moves along the curve x equal to e power minus t and y equal to 2 cos 3t and z equal to 2 sin 3t. Along this curve the particle moves. Determine the velocity. So velocity is nothing but the first derivative, acceleration is second derivative. Okay, so determine the velocity and acceleration at any time t and their magnitudes at t equal to 0. Now first we have to write the curve actually r of t equal to x of t plus y of t plus z of t. So therefore r vector at a point t is x of t into I vector, that is e power minus t into I vector plus 2 cos 3t into j vector plus 2 sin 3t into k vector. So this is a r. So auxiliary velocity is nothing but we have to differentiate r with respect to t. So that is dr by dt. So dr vector by dt is nothing but you have to differentiate term by term. So derivative of e power minus t with respect to t is minus e power minus t into I vector plus derivative of this is actually cos is nothing but minus sine and 3, therefore 6 minus 6 sin 3t into j vector, and this one is plus derivative of sine is cos 3t into k vector. So this is a velocity at any time t. If we take any point t, this is the velocity. Suppose and then we need magnitude, their magnitude. So at a point t, therefore what is the magnitude? First you have to evaluate what is the velocity at a time t equal to 0. So if substitute t equal to 0, we will get e power 0 is 1, therefore minus I vector, sin 0 0, cos 0 1, therefore finally we get 6 times k vector. So this is a velocity at time t equal to 0. Therefore, what is magnitude? So magnitude is nothing but square root of the coefficient. So usually what is the modulus of r is nothing but square root of x square plus y square plus z square. So this is a magnitude. Okay, so here x equal to 1 and y is 0, z is 6. Therefore, the magnitude of velocity is square root of 1 square is 1, 6 square is 36. Therefore, square root of 37 is the magnitude of the velocity at the point t equal to 0. Next, we got to find the acceleration. So acceleration nothing but you got to differentiate that again. So that is d square r vector by dt square. So already we know what is this. Again you got to differentiate. Therefore minus minus plus e power minus t into I vector. And then derivative of sine is cos, and then 18 cos 3t into j vector. And then derivative of cos is minus sine, therefore minus 18 sine 3t into k vector. So this is acceleration at any time t. Now we need a magnitude of acceleration. Therefore at time t equal to 0, therefore d square r vector by dt square at t equal to 0, we get I vector cos 0 1, therefore minus 18 j vector, sine is 0. So this is the acceleration at the point t equal to 0. Now what is the magnitude of acceleration? Magnitude of acceleration at the time t equal to 0 is square root of 1 square plus 18 square. So what is 18 square? I think 3 to 4. So therefore square root of 3 to 5. So if you simplify this, maybe we can write 25 times 13, therefore 5 times square root of 13. This is the magnitude of acceleration. Okay, so that's it. So acceleration, so velocity is nothing but you have to differentiate the first derivative, acceleration is second derivative. Okay. Next we define what is gradient and then curve and then divergence. There are 3 topics are there. So what is we are going to discuss gradient, curve and divergence. So here we have to define what is a scalar valued function and then vector valued function, or scalar valued function. And so first we define what is scalar point function. Scalar point function, and then we define what is vector point function. So scalar point function is nothing but in the region, if we take any point, we have to correspond to a number. So if you take any point in the region plane or R3, so if to each point x, y, z in the region of a region or in the plane, in space, not plane, in space, there correspond to a number. We have to assign to each triple, you have to assign some number. Okay, maybe some particle is moving in the plane. Okay, suppose look at, suppose maybe I write the definition, then we can explain. So there corresponds a number. Each triple we have to assign some number or a scalar. A number we can call our scalar pi. But this pi depends on this point x, y, z. That's why I am writing here. Okay, such as this pi function is called, then pi is called scalar valued function. Is called a scalar point function. And then sometimes called a scalar field. Okay, we will discuss later. So what is the meaning of this? What is a scalar point function? If we take any point in the plane, we got to assign some scalar. Okay, so maybe we discuss some example of scalar point function. Suppose we have a rod. Suppose you can see some rod is in the three-dimensional space. Suppose you are heating somewhere. Okay, suppose you are you got to heat this rod one side. Okay, so therefore you can pick any point x, y, z. We can talk about the temperature of this point. Okay, how much temperature at the point. So we have to assign this point to the temperature. Okay, so temperature of the point. So therefore for each point the temperature may be different. Okay, suppose if we take this point, we have to assign some temperature. So therefore the temperature is the function. So temperature is just number. For each point we have a number. That number is nothing but temperature of the point. Okay, or if you take the pressure, so each point there is some pressure, so we have to assign some pressure. The pressure is some number. Okay, so these are all scalar valued function. For if you take any point in the plane region, we have to assign some scalar. So such a function is called scalar point function. Okay, so the domain is R3, but the codomain is R. That is, we take any point in the region, we have to assign some scalar. Here the scalar is temperature. If we take pressure or anything. So similarly, we can define what is vector point function. If you take any point in R3, we have to assign some vector. So usually what vector means what? It has both magnitude and direction. So scalar means what? It has only magnitude, there is no direction. Vector means what? It has both magnitude and direction. So we can take okay, now this is an example for a scalar valued function. Scalar point function, not valued function, scalar point. Anyways, it's scalar valued, but we say scalar point function. Similarly, we define what is vector point function. Vector point function. So given any point in the space, we got to assign some vector. So that is a vector point function. Okay, so simply I can write, if we take any point x, y, z in the plane, we got to assign some vector. Such a function is called vector point function. So what is an example? Again, if you take some something, suppose some flow moving, suppose some water is moving. Okay, suppose maybe you can look at this, some water is moving. So we have to assign, if you take any point in this moving, you have to fix some point x, y, z. So I am talking about what is the velocity of this point. Suppose something is moving, flow is moving. Suppose it's crossed the point, this point, maybe you can call P. Suppose this flow crossed the point P. Now I check that at what is the velocity of this at the point, this one. Suppose otherwise, suppose some if you fix some point here, suppose some bike is moving. This actually assume that this is a road. Okay, some vehicle is maybe you can look at some vehicle is moving, running this road. So maybe the velocity may be different because it's very difficult to travel the same speed. Okay, maybe sometimes the speed is very slow or speed is high. So I pick this point. At that point, we have to check how much speed the vehicle is traveling. So I assume that the velocity, how much velocity. So that is I assigning that point to velocity at the point. At that point, what is the velocity? So this velocity have both magnitude and the direction. How many speed it travels and then which direction it moves. So all the things. So therefore, this is a vector valued function. If you take any point, we have to assign some vector. So vector means it has both the magnitude and the direction. Okay. This is an example. So usually we denote f, capital F vector, f vector of x comma y comma z. But in the scalar value, we just denote pi of x, y, z, because it has only magnitude. But here direction, that's why we put some arrow on the top. So this is a vector point function, scalar point function. Now we define new function that is called gradient. And then one more thing, what is the level surface? So the next definition, what is the level surface? So level surface is nothing but, if you know the scalar point function pi of x, y, z, you take this constant equal to take some constant. So this equation is called a level surface. If you vary the constant c, you will get different level surface. Okay. So the level surface is nothing but the equation pi of x, y, z equal to c, where pi is a scalar point function. Okay. Now, where here I can write where pi is scalar value, a scalar point function. Scalar point function. This is a level surface. Now, for each for a scalar function, we have to assign we have to operate something, and then for vector point function we have to assign something, that is we called gradient. So gradient we can define for scalar point function. So that is gradient of scalar point function. Scalar point function. So suppose we have a scalar point function pi. Okay, this is a scalar point function. This is a function of x, y, z, but it's a scalar point function. Only magnitude, there is no direction. Now the operator I am going to use delta is nothing but just I vector into dou by dou x plus j vector into dou by dou y plus k vector into dou by dou z. So this is the operator. Okay. Now the gradient of this function is denoted by del pi. So del pi is nothing but you have to operate the pi to the each function, each coordinate. Therefore I vector into dou pi by dou x plus j vector into dou pi by dou y plus k vector into dou pi by dou z. Therefore this is a vector actually, because we put I vector j vector, right? But this pi is scalar function, but if you operate this del, we get a vector function. So this is we define gradient of pi. So usually we define gradient of this scalar point function is del pi, where del pi is a vector function. So given any scalar function, we have to assign some vector function. That assigning is del pi. Okay. So this actually this operator is called is a vector differential operator. So this del is called vector differential operator. Vector differential operator. Now the gradient is del pi. Now the next definition, directional derivatives of a scalar point function. So in the beginning we define what is the derivative of a vector function, R vector. Okay, so we define here what is the derivative of vector function. Now for scalar point function, we have one more meaning, that directional derivative. Okay, not a derivative, this is called a directional derivative of a scalar valued function. Directional derivative. Directional derivative of a scalar point function. So direction means there is some direction is there. Okay. So suppose we have assume that we have some scalar point function. Let pi of x, y, z be a scalar valued function. Be a scalar valued function. Scalar point function in the region or something. Okay. Now what is the, suppose I want to find the derivative, directional derivative at the point P. Okay. So that suppose I am taking a look at the picture. Suppose we take some region R. So the function is defined from this R to real number R. Okay. Okay. This actually this is a function. This is a region R. The function is defined. The scalar function defined from R to R3. That is, we take any point x, y, z is assigned to some scalar. That is a scalar point function. Now, if you take some point in the plane in the region R, suppose I take some point P. So we want to discuss about the directional derivative at the point P. The derivative of pi at the point P. Okay. So suppose if you take some neighborhood. So again there are so many ways to approach this point P, right? So suppose if you consider some neighborhood of P. So if you take any point around this Q, around this P, suppose I take some Q is point. Suppose this Q approaches to this, what happened? So suppose P is here, therefore we have an image for pi of P. And if you take Q here, we have a pi of Q is a image of this. So if Q approaches to this P, what happened? This P, this approaches to this or not. So that is a usual meaning of in the derivatives of function. Similar thing here. So simply we can say the derivative limit Q approaches to the point P, pi of P minus pi of Q, or pi of Q minus pi of P by PQ, the length of this interval. If the limit exists, is called, if it exists, then is called this value is directional derivative, is called directional derivative of the point P in the direction A. In the direction some A vector. Okay. So maybe this Q approaches to A in the direction, suppose I take A vector. Okay. Now otherwise we have some theorem that what is the directional derivative of a scalar point function at the point x comma y in the direction of unit vector pi is just del pi dot A. Okay. So that is a theorem. So the theorem is enough to check the directional derivative of a function. So what the theorem says, the directional derivative of a scalar point function, directional derivative of a scalar point function pi at the point x, y, z, at a point something, some x comma y comma z in the direction of unit vector, direction of a unit vector A vector is given by, just you have to find the gradient del pi and then take the dot product with this vector A. So del pi dot A, this is the directional derivative of your function pi in the direction, in the unit direction a. Okay, so this is the directional derivative of your function. Okay, now this differential operator satisfies some properties. There are some relation, maybe some of them I will write. So if you take the scalar, if you operate the direction vector differential operator with some c is always 0, where c is just constant. If c is constant, then del c is 0, and if suppose del of some c times pi, pi is a scalar point function, but c is a constant. This is nothing but c times del pi, where c is constant and pi is, so whenever you operate del, that should be scalar point function. So we can operate del only for scalar point function, the dot product here. Okay, so here pi is scalar point function. Suppose you have two scalar point function, what is the del of pi plus some psi? Both the pi and psi are scalar point function. This is nothing but del pi plus del psi. And then fourth one, suppose product of two thing. So del of pi into psi is nothing but you have to fix first pi and then operate del to the psi plus psi into del pi. And if you take the quotient of two scalar point function, and what is the operator? Del of pi by psi is nothing but same thing, pi square, fix phi and then del operator del pi minus pi into del psi. So this is a thing. Okay, so maybe quickly we solve something to find a gradient. So exercise, suppose the function is given if pi of x y z equal to x square y plus y square x plus z square. So this is a scalar point function. There is no ijk here. Okay, this is just a magnitude. There is no direction. Therefore, this is a scalar point function. Find del pi. Find del pi at the point 1, 1, 1. At the point 1, 1, 1. So how to find that? You have to differentiate what is del pi. So del pi become a vector, okay, but pi is not a vector, but del pi become vector. So this is nothing but I vector into dou pi by dou x plus j vector into dou pi by dou y plus k vector into dou pi by dou z. Therefore this is equal to I vector into, if you differentiate pi partially with respect to x, we get the first term we have 2xy, the second term we have y square, the third term is 0, plus j vector into, if you differentiate y, we get x square plus 2xy, plus k vector into, if you differentiate with respect to z, we get just 2z. So this is del pi. Okay, now what is the value at the point 1, 1? Substitute x equal to 1, y equal to 1, z equal to 1. So therefore del pi at the point 1, 1, 1. So therefore this is actually 1 and then 3. So 3 I vector. This also 3 j vector, but this is 2 k vector. If substitute x equal to y equal to 1 equal to, they will get this one. So this is a del pi at the point 1, 1, 1. Okay, this is the gradient of a scalar point function at the point 1, 1, 1. Okay, so the next maybe we will do one more thing. What is the directional derivative of your function, scalar point function at the point? So the next exercise, find the directional derivative of the function x y z minus x y square z cube at the point 1 2 minus 1 in the direction of the vector I vector j vector plus minus 3k vector. Okay, now here pi of x comma y comma z is that things. So solution, the pi function is x y z minus x y square z cube. Now what is del pi? We need del pi because the directional derivative we need this one. So I vector into the partial derivatives of x. Therefore the first term we get yz, the second term we get y square z cube plus j vector into derivative of y, therefore xz minus 2xy z cube plus k vector into z, therefore xy minus 3xy square z square. So this is a thing, this is del pi. Now we have to in the direction unit vector, but this is not a unit vector. So this is our vector a. So what is a? A vector is the given vector I vector minus j vector minus 3k vector. So how we will check this is a unit vector or not? You have to take the magnitude. If the magnitude is 1, then that is a unit vector. So what is the magnitude of a? Magnitude of a is square root of 1 square plus 1 square plus 3 square is 9. Therefore square root of 11. Therefore 11 is not 1. So therefore we get a new vector. If you divide by the given vector by the square root of 11, you will get a unit vector. So we'll get a new vector n. We can write n vector is nothing but a vector by this modulus of a vector. If you take these, so that is I vector by square root of 11 minus j vector by square root of 11 minus 3 by square root of 11 into k vector. Now if you find the magnitude of n, that should be 1. Okay, we will check what is the magnitude of n. Square root of 1 by 11 square, that is 1 by 11 minus 1 by 11. Okay, minus minus plus, what will you get? 9 by 11, right? Because square root of this we get 9 by 11. So actually this is plus, because everything x square plus y square plus z square. If you take square everything cancels. Therefore what you will get? 11 by 11. That's nothing but 1. So this n vector is a unit vector. Now, but we have to take the directional derivative along the unit vector, but the given vector is not unit vector, so we have to reduce the unit vector. So unit vector means what? The length should be 1. Suppose if you look at in R2, okay, better I look at the R3. Suppose A is somewhere away from 0 or away from 1. Okay, suppose A is here, but 1 is here. So what we have to do? We have to divide the length of this vector. You will get new vector here. This n vector is nothing but a vector by norm of a vector. Okay. So if you normalize the vector by its norm, you will get a unit vector. So now what is the n vector? This is the n vector. Now find the directional derivative along this point. So directional derivative, that is del pi dot n vector. After that you got to substitute the point 1 2 minus 1, because at the point 1 2 minus 1. So you take the dot product. So you will get so what is this? Look at here. So here the x value is 1 by root 11. Here the dot product is 1. Therefore if you take multiply with these two, so we will get 1 by square root of 11 times the first point, y is at y square, maybe I can write y is at minus y square is at cube plus again 1 by okay, minus is there, okay, minus 1 by root 11 into xyz minus 2xy z cube, again minus 3 by root 11 times xy minus 3xy square z square. Now substitute x equal to, now we need the directional derivative at the point 1 comma 2 comma minus 1. Therefore substitute x, so if you can take 1 by square root of 11 outside from all the term, substitute x equal to 1, y equal to 2, z equal to 1, therefore the first term we have minus 2. Here
So your voice breaking, sir.
Okay. Now is it okay? Okay. So if you substitute here, what you will get? Minus plus, I think you will get 4. In the first term you will get this term. Here you already take 1 by square root of 11, therefore minus is outside. 1 minus 1, therefore minus 1, and this should be 2 and minus 4 plus, I think 4. And here we have minus 3 times, so minus 3 times 1 minute, okay, so 3 times if substitute x equal to 1, y equal to 2, therefore this is 2 minus I think this 3, 4, 6, I think 6. So that's it. So finally 1 by square root of 11, and this is 2, and this is 3 minus 3, and this is actually minus 4 minus plus 4, 12. So therefore 14, therefore 11. So otherwise I did some mistake, I think so. Okay, this is actually 12, not 6, because 2 square is things. So therefore this is actually minus 10, and then 30. So this is 29 by square root of 11. So this is the directional derivative of a function pi in the unit direction at the point 1 to minus 1. Okay. Now what is the maximum value? You take the square root of the gradient. Okay, modulus of the gradient is the maximum value. Okay, so what is the maximum value of the directional derivatives? You have to take the modulus of the del pi. So modulus of del pi is maximum value. The directional derivative at the point. Okay, you can substitute. Maybe we will solve some problem. So after you find the directional derivative, you take the modulus, you will get the maximum value. Okay, sometimes they will ask what is the maximum value of a directional derivative at the point. Okay, sometimes they will not give the direction, they will give only the points. You have to substitute the points and then you have to find it. So the problem is find the maximum value of the directional derivative of the function pi is 2x square plus 3y square plus 5z square at the point 1 1 minus 4. So first you have to find the del pi. So pi is given, so therefore del pi we can directly write del pi equal to I vector times 4x plus j vector times 6y plus k vector times 10z. So this is the del pi. Now at the point 1 1 minus 4, what is the value? So del pi at the point 1 comma 1 comma minus 4. So substitute 1, we have 4i. Here also 6j, but minus 4 is minus 40 k vector. Now you take the square root, that is del pi. So maximum value of the directional derivative is, direction is not given. Okay, so therefore at the point is just nothing but square root of the maximum value is maximum values of del pi at the point 1 comma 1 comma minus 4 is, you have to take the square root of 4 square. 4 square is 16, 6 square is 36, 40 square is 1600. If you sum this, you will get a square root of 1652. So this is the maximum value of the directional derivative at the point, this one. Okay, so for we define gradient of the scalar point function. Okay, so maybe in the next class we will discuss the divergence and then curl of vector point function. So for vector point function, we have a two operator, one is divergent, another one is curl. But the scalar point function, we have only operator, that is gradient. But the gradient gives some vector. Okay, we will discuss the next class.